So, welcome to this first episode of a Capgemini series on quantum computing, talking about bits, neurons, and now especially qubit. We will work together today with IBM to listen to one of their speakers to talk about quantum computing, giving an overview of the technology, but also the potential application. My name is Michiel Boreel. I am the CTO of Society, but today, more importantly, I am the host for today. And so, to have this discussion today, I have three guest speakers with me, which I would like to introduce. So, first, Gilad Ben-Shach, very welcome to you, Gilad. Then also from IBM, we have Cor van der Struijf. Cor, welcome. And then a colleague from Capgemini, Julian van Velsen. Maybe to give an introduction to the audience, maybe you can introduce yourself and also tell me what you have with quantum computing. So maybe first, Gilad, you want to go and answer.
Sure. Thank you, Michiel, and thank you for having us here today. My name is Gilad Ben-Shach. I'm a physicist by training. I did my PhD in condensed matter theory of topological quantum systems. And then I've spent some time as well in the consulting world and data science world. And today at IBM, I lead our quantum ecosystem program, which is both how do we engage with quantum computing startups, but also how do we engage with partners like Capgemini to plan for a future where quantum computing will be useful to our clients and to your clients, and how can we work together to be ready for that day.
All right. Thank you very much, Gilad. Cor, tell me who you are and what do you have with quantum?
Okay, thank you, Michiel, and also welcome to be part of this whole event. So, what's my background? Also on PhD in physics. So I did it on electron spin resonance and more precisely protein dynamics. So my dream with quantum computing is that we maybe one day can solve it. We then do the calculations that are needed for protein dynamics. I work now as a quantum ambassador at IBM, so helping organizations like Capgemini to adopt and also to learn about quantum computing, what it can do, and how it can solve all kinds of problems.
All right, thank you very much, Cor. And then, of course, last but not least, Julian, my partner in crime, as I call him. Julian, introduce yourself and tell me what you have with quantum computing.
Yes, thank you, Michiel. Happy to be on this call. Foremost, what I have with quantum technology is I'm just enthusiastic about this whole field. It's very rapidly moving. I feel like this is the moment where we are going from laboratory into application, and it's a revolution. It's a revolution that they call the second quantum revolution. While the first brought us the laws that govern the universe, the second one is giving us all kinds of different technologies. And I think we are at the tip of the iceberg. We have seen the first few things yet, and there's much more to come. So that is what I find fascinating and why I'm really enthusiastic about this field. Okay. Within Capgemini, Michiel and I work together to work on the services, but also to grow the community. So I hope this reaches as many as possible people.
All right, thank you, Julian. So to kick us off, maybe Gilad, you can first answer me this question. So before you explain what quantum computing actually is, can you tell me whether or not quantum computing is new?
Sure. So quantum computing as an idea is not new. What is new is that quantum computing is now available over the cloud and accessible to users anywhere, and the barrier to entry continues to be lowered and lowered over time. And hopefully over the course of the next hour, I will help convince you of some of that. And in our coming webinars as part of this series, we'll go deeper into that topic as well, and how it is time to engage. With the caveat that quantum computers are not yet useful, where by useful we mean can do something any better than your existing computational techniques can do. But as we'll also cover, there is a lot to learn, and the technology is advancing extremely quickly and has come a long way in the past decades, and especially in the past couple of years. And so now is the time to start to learn and engaging so that you are ready to use the technology when it is market ready.
All right. So can you start explaining where did it come from? How long is IBM already working on this, Gilad?
Sure. So IBM's been involved for many years in various flavors, including having hosted one of the first conferences on quantum computing, when it was the term and the idea of quantum information was first coined. But I'd actually, if we can jump to the first slide, I want to start with an old picture. On the next page, please. Thank you. So here, to say on the left, you see an old ENIAC device, one of the first classical computers, and we've started adding the word classical to describe computers that we know, to differentiate them from the quantum computers we'll be talking about going forward. And on the right, you see an early IBM quantum system. And I put these up against each other not to say that the two devices are similar in power or similar in how they work, but to say if we were to go back to the 1940s and 50s and ask what will computers be used for, it would have been impossible to predict that they would power your cell phone and do all the many things we do with them today, such as host webinars on topics of new computing over the internet and record them. All of this we would not have predicted back then. And so similarly today, when we predict how will quantum computers be used, how will they be consumed, we have some fundamental physics principles and reasons to believe where there will be value and where there will not be value. But exactly how they will be consumed 40, 50, 80 years from now is pure speculation. And it's fun and exciting to be at this early stage of a brand new technology, which is not yet fully released, not yet fully adopted, still in the early research stages, but has a lot of exciting potential.
So, Gilad, I always like to make this comparison between quantum computers and classical computers because we're somehow back in time, right? We're at the same step in this revolution. Could you indicate, like, what is a relevant year in which we might be? Are we in the 80s? Are we in the 60s? How far is the development?
I think we are. So it's an interesting question to compare to because there's always the question of utility. So in the sense of what size problems can quantum computers handle, we're probably still much closer to the 40s. But the challenge now is that the benchmark we need to beat, the mark of success, is that a quantum computer is not useful until it is better than existing classical techniques. So classical computers you can compare to pen and paper, and anything that can be done faster than you can do by hand is already an achievement. Today, we cannot compare quantum computers to say, can they do faster than I can do by hand? We have to say, can they do better than my laptop? Can they do better than my HPC system? And that's a much higher bar to meet. And so because of that, it's interesting to try to make those comparisons. And as well, I'd add that the way things are being developed is different from the beginning. Cloud services are being offered. Quantum computing is being offered as a cloud service from day one. Building in components and pieces that can be subbed in as little blocks into your program is part of how we're approaching quantum computing from day one. Mm-hmm. Thinking about tools and microservices is fundamental to this from the beginning. And so it's very different from classical in that sense, where a lot of things that we've only added to classical computing in the past decade or two are being integrated into quantum computing from the very beginning of its commercial deployment.
Now, quantum computing, of course, is not new, right? So there's already a whole road behind us on where that get us where we are today. Can you quickly describe what that road looked like?
Sure. So if we can jump to the next slide, please. I'd like to start in the 1930s, and this is now into the first few years of quantum mechanics. And particularly like to call out this paper you see at the very beginning of this timeline, referred to today as the Epr Paradox. E, P, and R are the initials of the three authors of this paper. E is for Einstein, who is famous and known to all of us. P and R were lost to the history books outside the physics classroom, but they are Podolsky and Rosen. And the interesting takeaway from this paper is that Einstein and his colleagues argued that entanglement, which is a principle of quantum mechanics that we will talk through in the coming slides, could not make sense. It could not be right, and quantum mechanics had to be wrong. And it took until the 1960s for Bell to publish a paper we now refer to as Bell's inequality, which gives you a way to actually test, is Einstein right or is quantum mechanics right? And then years later did we actually perform the first experiments and validate that Einstein was wrong and there is no paradox, and quantum computing is actually correct. As you see into the 70s and the 80s were the beginning of quantum computing in theory. We fast forward to 2007. There were some initial experiments of quantum computers before then, but the technology that we use today at IBM was first developed in 2007 at a lab at Yale University. And fast forward to 2016, so just the past couple of years, where IBM was the first to make quantum computing available over the cloud. And this is really exciting. Instead of needing a multi-million-dollar budget and a team of experts to actually build the quantum computer in your lab so that you can then use it, you can now access for free real quantum hardware and start to experiment with programming it and writing algorithms and using it as a real research tool.
So, Gilad, I really like this image because I think it shows that nothing comes in a day. I mean, it's a very rich research base that supports this technology. At the same time, in the past couple of years, a lot has been happening. And I think you also just mentioned that especially the past few years have been great breakthroughs. What would you say is one of the bigger milestones of the past 3 years? And especially because I think most of our listeners today have heard about quantum supremacy. Do you think that should be in the image?
So, good question. There have been a lot of milestones in the field, and probably too many to fit onto this slide, even if we wanted to put them all in. I will talk later in this hour about milestones in terms of number of qubits launched, milestones of quantum volume, some achievements in specific algorithms. Quantum supremacy specifically, it refers to an experiment that was proposed by theorists. It was performed by a team at Google. It is an extremely exciting scientific result, but it is distinct from what I will define as quantum advantage shortly, which is where we define to be when quantum computers are actually useful to solve a commercial problem any better than existing techniques. Quantum supremacy refers to a very specific problem that is not useful for anyone in industry. It is a specially designed problem, designed such that a quantum computer should be good at solving this problem and a classical computer should be poor at it. And so it is a very impressive scientific result. In our view, it does not have the industry relevant application of a lot of the other goals that we are currently chasing. And I think that will mark a turning point in the field when somebody crosses that line and a quantum computer is actually useful for an industry application.
Okay. So let's continue on the journey. Gilad?
Yep. So on the next slide, I think we put that into perspective and redefine the timeline in terms of 3 key eras. And so the early days are what we call quantum science. And this is when there were the original debates about quantum mechanics, the ideas coming together about quantum computing, the first experiments in labs. And in that phase and that era, quantum computing was only accessible to experts at academic institutions. In a future world, which we have not yet arrived at, we will hit quantum advantage, where quantum computers are actually useful to solve real-world problems, and clients have a need to be using them. Today, we are in this middle phase we call quantum ready, where quantum computing access is being democratized. People around the world can have access to quantum computers for their research. We are not yet at the stage where they are impactful for real work, but there is a lot of engagement, enablement, and learning that is required to get there, and now is the time to do it. Because the quantum advantage line, we don't know exactly when we will cross it. We expect to cross it in the coming few years, and we are going to hit that very quickly. And we do believe it will be a light switch moment where the technology will cross a line and be ready for real impact, and you and your clients need to be ready for that moment.
Okay. So another question for you, Gilad. So how are superpositioning, you already mentioned it, and especially entanglement, the basics of quantum computing? And do I need to be a quantum physicist to understand quantum computing?
Good, very important question. Let me start with the second half, and this will become more clear in the coming slides, and then take a step back to the first part. Today, to use quantum computers, you do not need to be a quantum physicist. You do not need to be an expert. The key skills required, and we'll touch on these in the coming slides and show why they are relevant, are an understanding of probability theory, an understanding of linear algebra and how to multiply matrices together and work with vectors, and basic Python skills. These are, in our view, part of the standard toolkit of most engineers, developers, programmers, etc. It's part of a standard undergraduate degree in computer science, in physics and engineering, math, etc. And so we are confident that many, many people can easily engage in quantum computing. There is still a lot of fundamental research to happen, which does require the more expert niche skills of a focus in quantum computing, but we think a lot of the interesting work today can be done by many more. Before going to the level of abstraction where you don't need to understand the physics, I think it is helpful to take a little detour and talk through some of these principles, as you mentioned. Superposition, entanglement, I don't think I have it written on the slides, but interference is an important concept as well. And so if you jump to the next slide, I'm happy to just run through some of these definitions and give you a little bit of a sense of how quantum computing is different. And in particular, we'll go back and make sure we answer why Einstein was so confused by some parts of quantum physics. So classically, we talk about the bit being the basic information unit of information, which could be a 0 or a 1. The quantum bit, we call a qubit, is also 0 or 1 whenever you measure it, whenever you try to read out its state. But it can be in what we call a superposition, which although some define as being both 0 and 1 at the same time, I prefer to think of it, my interpretation of the quantum mechanics here is that it is defined to have a probability of being 0 or 1, and it is not really either while in that state until you measure it. A classical analogy of what this could feel like is imagine spinning a coin in the air, a coin that has two sides, heads and tails. While spinning, it is wrong to say that the coin is both heads and tails, but it is also impossible to really say, is it heads or is it tails? The coin has a 50% chance of being heads and a 50% chance of being tails, and it will be one of them when it lands on the table. Similarly, in the quantum case, we can write this here, you see at the bottom, as the options instead of heads or tails are 0 or 1, and my state is defined by having a probability a squared and of being 0 and a probability b squared of being 1. And so if a and b are equal, then it's a 50-50 chance like my coin, but I could also have my system in a state which will be 100% 0 and 0% 1, or vice versa, and define that well. And we
So
can...
I think that's great, right? Because it shows that it's a very probabilistic theory, and I think a lot of people on the call are also maybe from insights in data. They have experience with different AI models, and they tend to have a good background in statistics. Is this also something that you guys look for in your team, that because it's a probabilistic theory, that a good knowledge of statistics is maybe even more important than physics?
So in our team today, we are mostly quantum computing experts working on the topic, so PhDs in quantum information theory or related fields. But as a general skill required to engage, as we start to build a broader workforce for the future, as our clients start to hire their own teams, 100% yes, this is an important and required skill. It's comfort with probability and statistics. And we won't talk about in much detail today. I think we'll cover it a little bit more in the next section. But because of the nature of these probabilistic systems, and again, they have definite probability. So the system is very well defined as having a probability of being 0 and a probability of being 1. But then you sample from the fixed probability distribution to determine what those probabilities are. So if I tell you I have a coin that is 50% 0, 50% 1, you can then flip it and see what you get. But I can also give you a coin and you can flip it many, many times in order to tell me I've decided this is a fair coin that has 50% chance of being heads and 50% chance of being tails. And so being comfortable with these ideas from probability and statistics is essential to understanding quantum computing and to being able to start to use it. But again, as pointed out, this is very different from being an expert on superposition and entanglement and other core principles of quantum mechanics. It is just a probability that is really essential here to start to use these systems.
So what about superposition? What about entanglement? Now I'm getting confused myself. What about entanglement?
No problem. If we can go back to the superposition slide just for one last second, one comment to add for the experts here. So we represent, the figure you see on the right is what we call a block sphere, and a representation of the state of a qubit. And we've put 0 at the top and 1 at the bottom. And because your total probability must always equal 1, you are 100% going to be in one of the states somehow. We are constrained to be on the surface of a circle, going around between 0 and 1. But if you look at it, and if you listen, we call this a sphere and not a block circle, and you see that there's also an equator to this sphere. The reason for that is because we allow A and B, these weighted probabilities, to actually be complex numbers, and they can have relative phase to each other. This starts to get a little bit more complicated. We will not go into detail on that today, other than to call out that ultimately the game of probabilities is to use the fact that A and B can be negative through these relative phases to have sometimes the probability add up and sometimes to subtract and cancel out. This is what we would call interference, and this is how you eventually get the ideal answer eventually becomes the most likely answer with the highest probability, and therefore if you measure the system enough times, you will get the correct answer out. If we jump to the next slide, Michiel, I'm happy to answer your question a little bit about entanglement. And what you see here are fuse switches. I took these pictures at the fuse box at my apartment here in San Francisco. On the left, you see 2 completely normal fuses. On the right, you see 2 fuses that are connected by a little plastic beam. And the idea here is that on the left of the page, if I were to cover one of the fuse switches with my hand and let you look at only one of the 2, you would have no idea if the other one is also up or down. So if I cover one and you see that the fuse on the far left is now switched to on, you have no idea that its neighboring fuse is whether it's on or off. On the right-hand side, if I cover the fuse on the far right and show you its neighbor, which is on, you know that the fuse on the far right must also be on because they're connected by this little beam, and you know they're connected, and therefore, if one is up, they are both up, and if one is down, they are both down. Similarly, entanglement in quantum mechanics is to say that 2 quantum particles, or in our case 2 qubits, have their states so intrinsically tied that if I know the state of one, I know the state of the other. And so a way to think of this back to the 0s and 1s is that if I have 2 qubits, I have 4 possible states, 0, 0, 0, 1, 1, 0, 1, 1. And if they are entangled, I would know that if my state is 0, your state is 0. If my state is 1, your state is 1. And the cases of 0 and 1 or 1 and 0 are not allowed in this case. What makes the quantum case very different from the classical case is that if I were to take these 2 fuse switches on the right and start pulling them further and further apart in space, eventually I would break that plastic beam and they would no longer be connected. They would be completely independent once again. In the quantum case, I could take my 2 qubits, take them to opposite ends of the universe, and they are still going to be entangled. They are still going to be tied in the same way they were originally. And that was the part that really bothered Einstein and his colleagues in that original paper, of how can I have 2 things that are so far apart that I could know the state of your qubit faster than light could travel between us and actually send a message telling you that I had made a measurement. And so that's a really interesting problem. It bothered many people for a long time. And as we start to move on in this talk, it is not essential to understand how entanglement is a true principle of quantum physics. And it is important to understand that even Einstein found this confusing. And so you are in very good company if you look at this and you scratch your head and say, this is different than how I've understood the world. This is different than how I've thought about computers before. It is different. It is new. But in my opinion, that is only the one piece of why it is also so exciting. So if we jump to the next slide, please, to sort of build how these all come together. In a sense, we can say that superposition allows the creation of exponential number of basis states, and together with entanglement then allows for parallel exploration of these states and provides a computational power. So a way to think about this, if we define n to be the number of qubits, you have 2 to the n basis states. What that means, if we switch to the next slide, in the case of 1 qubit, you see at the top, we have again 2 basis states as we defined before, 0 and 1, and they're weighted by A and B. In the case of 2 qubits, we have 4 basis states as we were just defining previously, 0, 0, 0, 1, 1, 0, 1, 1. In the case of 3 qubits, you have 8 states, and you see those listed out below. If you pause for a moment and you say, wait a minute, if I have 3 classical bits, there are also 8 possible states I could write out. And those 8 possible states look exactly like the 8 you see here, 0, 0, 0, 0, 0, 1, etc., through 1, 1, 1. That is correct. The distinction is that in the classical case, my 3-bit register will be in one of these 8 states. Whereas in the quantum case, I can set my quantum computer to be in a state such that it has a probability A of coming out in 0, 0, 0, B of being 0, 0, 1, C of 0, 1, 0, etc. And so I could create this state of weighted probabilities where A through H are, again, complex numbers. Now, the way to think about this is I can represent these letters, these probabilities, as a vector. So let's go back for a second to the 2-qubit case. For simplicity, I can define a vector which has 4 entries, A, B, C, and D. And these represent the weights as you see them here. In that case, what a quantum algorithm is effectively doing, I will be multiplying this vector by different matrices. This choice of matrix is important, and that's how you write your algorithm. And the outcome is going to be a new vector. A matrix times a vector will give you a new vector with new probabilities, and those become the probabilities of your final state. And so this brings us back to the discussion from the very beginning of if you are comfortable with vectors and matrices and then your algebra, and if you are comfortable with the vector representing probability and statistics, you have the basic tools you need to start really exploring quantum algorithms without having to worry about the ideas of superposition and entanglement that we were defining on the previous pages. If we jump to the next page quickly, just to start to see how this grows, by the time you get to 50 qubits, and the largest IBM system on the cloud today has 65 qubits, so we've already passed this point, but by the time you get to 2 to the 50 qubits, you have 2 to the 50 basis states, which is over 10 to the 15 possible basis states. And so your vector is becoming extremely long, your matrices are becoming extremely large, and you are really starting to get into the world where classical computers cannot keep up in simulating these systems, in actually calculating these systems exactly. If we jump to the next page of 275 qubits, and I'll show you later that this is in our roadmap for the very near term, there are already more basis states than there are atoms in the observable universe. And so this grows extremely quickly, and we are excited by the potential of how we can start to leverage these tools for various applications that we'll talk about.
So that is quite an amazing number, right? I mean, only with 275 qubits, there's more states you can ever imagine, more states than are seeable in the observable universe. And then even if you put 1 extra qubit, you again double the amount of states that you can work with.
Yeah.
If you have that many qubits at your disposal, that many states at your disposal, why would we want to go to like 1,000 qubits or more than that? Isn't this enough to simulate the whole world? I mean, naively, you would think that, right?
Yes. So that's an important question that we will touch on in a different flavor a little bit later. The short answer is we will talk a lot about quantum computers being noisy systems. And because of that noise, you need ways to mitigate it and ways to deal with the noise. And one way to do that is to start to use many physical qubits to create what we would call a logical qubit. And so a classical analogy, which cannot be applied here, but I think gives you a good idea of the direction we're thinking. If I want to send you a bit, I want to send you a message of 0 or 1, but I'm afraid that bit might get confused along the way and be thrown into a state of error. I can instead send you 3 bits, which are all copies of the same number. So I could if I want to send you a 1, I will instead send you 1, 1, 1. And my thinking is that in the time of travel, it is likely that one of the 3 bits will get flipped, but unlikely that more than one will get flipped. And so when you receive my message, you will look for the majority rule. So if you receive a message of 110, you will assume that the 0 was the error because I only send you messages where all 3 are the same. In that sense, we needed 3 classical bits to represent one piece of information so that we would avoid errors along the route. Similarly, in quantum systems, we expect to actually need millions of physical qubits to achieve this kind of scale. And so these numbers are a little bit misleading in terms of how useful the quantum computer will be, but we do think it is important to get a sense of how these systems can scale.
Very good.
Yep. So if we jump to the next slide, just to bring this all together, I think we'll jump through a few slides very quickly. The next slide, which I don't see it up in big yet. If we go back to the one with says IBM quantum computers leverage these.
Okay, yeah. There we are.
Perfect, thank you. So IBM quantum computers leverage these fundamental principles of quantum mechanics that we've been discussing so far. And therefore, on the next slide, we will mention that these new machines require a new approach to programming, including new algorithms. And so in our next webinar, we'll talk a lot more about actually how to program a quantum computer. Here, I just want to call out that IBM supports 2 key interfaces. One you see on the left, which is a visual drag and drop, where each of these little shapes and boxes you can drag represents a matrix and one of the many steps of your circuit, of your quantum circuit, your quantum algorithm. And on the right-hand side, you see a screenshot of Qiskit code. This is our Python-based framework, and so this brings in the final third ingredient we were saying. In addition to linear algebra, probability, and statistics, you also need to be comfortable with how to program a computer generally. In our case, we're using Python. And then from there, it is straightforward to build toward quantum algorithms. If we jump to the next slide, briefly. So this is just to say that if you go to the website on the right, quantum-computing.ibm.com, you can open an account for free today and run, using Qiskit, actual code on real quantum hardware remotely over the cloud from the comfort of your home. IBM does also offer premium access, and I'll touch on this a little bit at the end, and happy to answer more questions later.
Okay, great. I think just as a heads up for next session, you mentioned we go deeper in this. For all the INDers, the insights and data, and the AI people and the programmers in there, if they access the quantum environment through this website next session, can they just get started? Is it that easy, or do you at this point still need some physics skills?
It is that easy. There's lots of documentation online. There are YouTube videos of how to get started with Qiskit. There is an open source Qiskit textbook available at qiskit.org. And I'll put that website on. If we go to the next slide, I think I have the link for that, how to spell qiskit.org. If we can make that slide big. And so you should have all the resources required to start to get your hands dirty. And in the next workshop, we will lead the group through the basics of actually getting set up and how to do that. And so...
And I can testify to the fact that it's not that difficult, because actually I went through a Qiskit course myself using these tools, and you can already start experimenting, and it will build your understanding tremendously. So I'm a testimony of how easy it actually is, Gilad.
That's great. I'm happy to hear it, and look forward to hopefully many more testimonials after our next session.
Yeah.
So here, this slide is just to say that Qiskit is our open source Python-based quantum computing framework. It is modular and extendable intentionally. It is built out of what we've been calling these elements for the different modules, although we're in the process of rebranding what they are called. But the point here is not to go deep into each of them. It is to say, first of all, that Qiskit supports many different levels of abstraction. whether you are a physicist and would like to be writing individual pulses of microwave pulses that you will send to the computer to actually really control the detailed workings, it enables that. Or if you are an applications user and you want to use at the more abstract level, you want to call existing algorithms and circuits that you will then run, you can do that as well, the way a data scientist might call existing functions from Python. And so it enables the whole range of the stack of how to engage with quantum computers. But I particularly want to call out at the bottom AIR, and I've highlighted the word simulator. So a quantum simulator is a classical program that uses your classical computer to effectively, explicitly multiply out the matrices that are needed for a quantum algorithm. And so this lets you calculate the exact solution to a quantum algorithm. The challenge is that quantum simulators cannot get very large. So for 20 or so qubits, we can still do that relatively easily. By the time you get to the 50 or so qubits, you are pushing the limits of HPC computing and using the Summit supercomputer. When you start to get much larger than that, you cannot simulate them effectively today. And so we are still...
So there are machines like Atos, for example, has this quantum learning machine, but there are many different shapes of this. So do you think that this will... What is the purpose of these kind of simulators once we pass the point of, this amount of qubits that can be solved classically?
So I think that the purpose of classical simulators, and as you say, there are many who have some in the market. IBM has a simulator available for free on the cloud. I view their utility to be learning how to write quantum programs. So as we will discuss, our hardware is noisy. Errors happen a lot. Our hardware has a queue. You need to wait in line along with others to run your code on that hardware. Simulators are typically much cheaper and more widely available. Our hardware is free, but cheaper from a time perspective. They are also simpler to use in the sense that they can be noiseless. And so in the early days of testing your quantum algorithms, it is helpful to test it on a simulator. The analogy I would give here is that as a graduate student writing code that I wanted to run, I would always first test my code on one core of my laptop before sending it to run on many cores of an HPC system. Because if there was going to be a bug, I would rather catch it early and quickly before I ship it off for 12 hours to run and then have to wait to see the answers I get back. Similarly here, the simulators can let you test algorithms early before you run them on hardware. Today, we are still in the world where simulators can do better than quantum hardware, but again, both are far behind existing classical techniques. The distinction is that we don't see a roadmap for simulators to really scale much beyond where they are today. I'm sure that with continued improvement, we can add a few more qubits to what can be reasonably simulated. We are not going to get to 1,000 qubits simulated and 10,000 qubits and millions of qubits. Whereas in the actual quantum hardware case, we are on a roadmap to get there, and we are optimistic that we'll continue to push larger and larger. And so, whereas the simulators will hit a plateau in the not-so-distant future, quantum computers are only beginning their rise in value and impact.
Okay. Now, you already alluded a little bit to it, Gilad, on this point of that we need to look further than only the simple number of qubits to get an understanding of the power of the quantum computer. Can you explain that a little bit?
Sure. So if we pull up the next slide, it should show a little bit about what we call quantum volume. And so as we've been mentioning, the number of qubits is not sufficient because noise is important. And so, one example of this is if you wanted to have a 300 qubit device today, we can go to the lab and make you a 300 qubit device. However, it will not be any more useful than our existing devices because as is, we don't typically leverage all of the qubits on a device due to noise, and a 300 qubit device would only be noisier because neighboring qubits are sources of noise for each other. And so the more qubits you have, the more sources of noise you have. So a metric we have defined at IBM to use for the short term, for the near term of comparing devices, rather than just going with qubit count, is something we call quantum volume. And so here in a schematic, you see on the x-axis, the horizontal line where it says qubit count is moving from 5 up to 500 qubits. And on the y-axis, you have error rate, where the further away from the bottom is low error, which is better. And so what you see is that the box represents the size of quantum volume, which in a sense is a measure of the power of the quantum computer. And by staying at high error rates, so close to the bottom, increasing your qubit count has no real impact. And similarly, at small enough devices like 5 qubits, continuing to lower the error rate will also not have significant impact. In order to get to the largest quantum volume, you really need to march along the diagonal in this chart. And so as I'll show you in the coming slides of our actual hardware development, this is what we're doing, but what it effectively looks like is we fix our qubit count, and I'll show you first 5, and then we march up in lower and lower error rates. Then we take a step to the right, which takes us to, in our case, I'll show you 20 qubits. Again, we take a step back, and it's a noisier system, and then we march up and make it less and less noisy. And that's how we are effectively trying to march along the diagonal. Let's take a step to the right, several steps up. Take a step to the right, which often pushes us back a little bit, several steps up. And we are optimistic that this approach is going to help us continue our roadmap of doubling the quantum volume every year.
So could you maybe reflect a little bit? So this approach, starting small and growing to quantum volume, may be a bit different than the approach that, for example, Microsoft has. They have the should be much less prone to errors, or maybe photonic quantum computing, or maybe for some particular noise sources, also trapped ions might be less prone to noise. Why particularly this approach?
So the Microsoft approach is something near and dear to my heart. That was my PhD focus. And there, in topological quantum computing, I think everything is distinct and probably not relevant for quantum volume because it is, as of today, we have still not demonstrated, we as the entire physics community has not demonstrated a single working qubit. And so the importance of noise there is not yet relevant. If we look at the other technologies, what's important here is that noise itself is not really the metric included. The way to think about quantum volume is across how many qubits and how deep, how many steps of my algorithm can I consistently run before I hit some noise threshold. And so what you end up seeing with a lot of these competing technologies that you've mentioned, as opposed to IBM superconducting qubits, is that you have more time to run an algorithm, but the algorithms run slower. And so ultimately, you cannot move much further down the steps because you have more time, but it takes you longer, and so you end up at the same place. That said, for a lot of the reasons you've pointed out, effectively both connectivity of the system as well as the having less noise, in the very short term, ion qubits are expected to outperform superconducting qubits on this metric. And so at IBM, we do believe that superconducting technologies are the route forward, and that's how we will scale into the future. But there has been some recent news, and we are excited by that news, that some of the large players in the ion qubit space have actually been setting new records for quantum volume. And from our end, we think this is great. We are very supportive that quantum volume is being used as a metric to define the field. We are excited by the research being pushed forward, but we do believe that ultimately superconducting qubits will be the winner in the long run.
So Gilad, can you explain to me, so you already said something about it, this kind of step-by-step evolution of both the number of qubits and then getting the error rate down and then moving up to this next step. Can you explain that a little bit more?
Sure. And so we pull up the next slide, and I'm going to run through these fairly quickly because I'm conscious of time. What you see here, each row represents a different device, with the oldest device at the top and the newest device at the bottom. And the y-axis, the x-axis, the horizontal axis here, is the gate error percentage for a 2-qubit error rate. And so the goal is to have gate errors as low as possible, so as far to the left as possible. And the y-axis in each case is a normalized distribution. And so what you want is to see a distribution that is as narrow and tall and as far to the left as possible. And you can see that in our early devices, these were fairly noisy. And as we push to newer and newer generations, these do move further and more narrow to the left.
Yeah, and then the Yorktown was the first one, and then the Vigo is the latest machine. That's what you're saying.
That is right. We actually have even more recent machines that have not made it onto this chart that are looking even better than Vigo. If we jump to the next page, similarly in the 20-qubit case, Austin was our first device and Bublagin was our last 20-qubit device. And again, you see a wide distribution of noise at the top, becoming better and better toward the left, right? More and more narrow and moving toward the left as we move down in time. The 20 qubits did not quite look as nice, but we've since shifted to focusing on a slightly new development of our 27 qubits, which you'll see on the next page. And here, again, the earlier generations were more noisy, and I think the improvement is not quite as stark, but we have been moving these devices more and more to the left. And in the terms of quantum volume, we've actually started at quantum volume 16. We show here those were the 20 qubits on the previous page you see again, but the three devices at the bottom here are the 27 qubits, and they continue to get better. We've actually since made software improvements for Montreal, and that has now become a quantum volume 64 device. But the data here is still from the original quantum volume 32 measurement. If we jump to the next page in a similar way here, showing the 53 qubit device, and again, just only one generation, which is fairly noisy. And so we've taken a large step to the right, and now again, we have to iterate on these larger devices. We've actually, I think the future generations of this are going to look like 65 qubit devices, but at 65 qubits now, we need to iterate and drive down the noise.
So maybe a stupid question, but when will you reach a quantum computer when there is no noise anymore? That is just...
So that is called fault tolerance, and I wish I knew. Hopefully in the coming few to more than a few years and not too long, there is a lot we think we can start to do before we really hit fault tolerance, but that is the holy grail. When we cross the fault tolerance threshold and noise is no longer an issue because we can handle it, that is when the world opens up to quantum computing.
So that's the breakthrough to look for the next couple of years, right? Yeah.
If you see that fault tolerance has been achieved, the field has crossed the line into right. There will be other points of important points in time before then, but that will be the big one.
Okay.
The next two pages actually show us quickly a little bit about how we're defining the roadmap. So on the left, you see an early version of Moore's law, and the right, you see what I was mentioning earlier, which is that we are on a track to double our quantum volume every year. We've actually hit the 2021 doubling already with the Montreal device this year in 2020, and we plan to continue to use this roadmap for the foreseeable future to continue to improve the quality of our devices. From a size perspective on the next page, because as much as I've been telling you that size itself is not important, quality of the qubits is essential, but back to the size story as well. So in 2019, we hit 27 qubits. As mentioning recently, we just, in the past few months, have hit 65 qubits. And our roadmap to get larger and larger is next year to hit 127, the following year to cross the 430 mark, and then by 2023 to cross 1,000 qubits. And we believe that if we can reach 1,000 qubits, we will have solved many of the fundamental problems required to have a path from there forward to 1 million and more qubits. And so each stage of this iteration, we will need to solve important research work, and we have teams working on all of them. And we believe that if we can hit this 2023 milestone, we will be in very good place to continue to deliver toward 1 million qubits and more.
So these are all fascinating, really fascinating developments, Gilan. So thank you for sharing that with us. So what is IBM offering in the field of quantum computing?
Great. So IBM is a full stack provider right now. And so what you'll see, I think there's a quick page just showing that everything from hardware to systems and services is part of what we are building and offering. And if you go to the page after that, there should be a picture of the IBM Q System 1. I think it's the next page from here.
Yeah.
Yep. So you've probably seen this picture in the press. You
can buy it, right? You can buy it and have it at home?
Not quite, but maybe one day. So the system itself is fairly large. I don't have the exact measurements, but it's probably about 2.5 meters wide and maybe 3 or so meters tall. And what you see here, on the next page, this is a very fancy casing. But sorry, if you go back for 1 second. Thank you. So you see this black tube in the middle. There's a glass wall on the right, and there's a black wall in the background. So if you jump to the next picture, we're going to look through that glass on the right. So it's a side view. That black tube is this now gray tube that's partly open in the middle. The black wall that you saw is the vertical line in between the left half and the right half, which look different from each other. And the quantum computer itself is a small chip living on a circuit board, living at the very bottom of that tube. And the bottom of that tube is cooled to 15 millikelvin, which is almost absolute zero. It is colder than it is in outer space. And what the reason for this, first of all, you need to cool down these systems for the quantum effects to be visible. But we go even colder than required to freeze out a lot of the potential sources of noise. And so if you make an analogy to your desktop PC, which has a CPU that might be a few centimeters by a few centimeters and a fan that is maybe 10 by 5 centimeters or so, here the quantum processor is even smaller than a typical CPU, and most of the system is effectively replacing your fan, and it's providing your cooling power. On the back in this rack, you have both the equipment required to achieve that cooling, as well as all of the classical electronics required to generate the microwaves that are sent into the system to actually control the quantum hardware itself. And we won't go into detail on that process today, but happy to do a more detailed webinar on how the actual quantum hardware works if the Capgemini team is interested in that.
All right. So tell me, so I'm, of course, as an engineer, fascinated with this progress and all the research that goes into it. But so why is everyone so fascinated by quantum computing?
So the very short answer is that quantum computers are predicted to be able to solve problems that are very hard classically. So from classical computation perspective, and I will not get into the debates of does P equal NP and what does hard really mean, but there is belief that there are problems that are easy for your computer to solve and there are problems that are hard for a computer to solve. Among the problems that are believed to be hard, such as factoring very large numbers, which is the basis of encryption, or simulating quantum mechanics, which is important for a lot of chemistry and biology research, that these are hard problems for classical computers, but quantum computers should be able to solve such problems much more effectively.
And are they hard or impossible, Gilad?
So there's a question of what you define as impossible, but if it would take longer than the age of the universe for a classical computer to solve it, it is in theory possible, but practically impossible.
Yeah, okay.
And if that same problem can now be solved in minutes on a quantum computer, then in a sense you have made the impossible possible. So I use hard from the complexity theory perspective, but it is practically impossible to do solve a lot of these problems today, and we are optimistic that quantum computers will make them possible to solve.
All right. So we are getting to the end of our time we have with each other. Maybe you can talk a little bit about the applications that you see for this technology, right? It's still early days. Lots of development has to take place. Lots of breakthroughs have to take place to make it practically valuable. But just look ahead a little bit of where do you see the most interesting applications of this technology?
Yep. So we see applications falling into three main buckets: simulating quantum systems, artificial intelligence or machine learning, and optimization or Monte Carlo work. And so if you jump to the next slide quickly, it has a list of just some of the partners we're working with and some of the problems in these buckets that we are covering today. But I'm going to jump specifically into three examples, one from each of these categories. Mm-hmm. So on the next page, we have a chemistry simulating quantum systems example. This is work we did together with our colleagues at ExxonMobil. And here they were trying to use a quantum computer to calculate the specific heat, the heat capacity of a hydrogen molecule. And so in the chart here, the green is experimental data, the green marks. The black is an exact classical solution. And then the blue and the red are quantum calculations. The red is the improvement that the Exxon team developed. And you can see that it's actually doing quite well. And so on one hand, and this is a theme I'm going to share across the examples, it is extremely encouraging that we have solved an actual chemistry problem on a quantum computer. And we've done it quite accurately. It was important to the Exxon team to achieve chemical accuracy, so to be accurate enough and close enough to the real solution that they could use it in future work. The catch is that we are doing it on the hydrogen molecule, which is the smallest possible molecule, something very easy to solve on your computer today. And so the goal here is now to extend these techniques to larger and larger molecules until we cross the threshold where we can solve molecules too large to solve numerically today. If we jump... Yep.
The problem that has been solved here is still a toy problem, right? I mean, the hydrogen atom is so small you can solve it on a classical computer easily.
Correct.
But still, there are loads of commercial partners in your IBM-Q network, and they're doing this for a reason, and probably not to solve hydrogen, the model itself. What do you think is the core reason why you have to do these experiments, and what is it that ExxonMobil learned from these experiments?
So I think the most important thing they learned was how to actually program a quantum computer. And one of the ways they were able to make this better is there is a classical optimizer that works as part of the circuit. And so you are effectively sending a quantum piece to the quantum computer, but there's also a classical piece happening together. And a lot of the algorithms today are hybrid, where you leverage both classical and quantum computing, each one at the right point of the algorithm. And so they were able to make improvements to this technique. And I think for a lot of our partners, today they're still considering the work to be open source and pre-competitive, but there is definitely a feel that if I engage in this early enough, I can start to own the algorithms myself. They can become proprietary algorithms and I can have an edge. The other part of it, as Exxon is seeing, Exxon is a great example of a company that scaled up extremely fast, but it still took a year to go from starting to learn to having these first results in the first paper. And so to wait for quantum computers to be ready, that would be a year lost to competition who would be ready to go on day one. And so Exxon and a lot of the other partners we work with are positioning themselves to be ready to leverage quantum computers on day one and not lose a year or more. So there are other problems that Exxon, as an example, are working on, which they started at the very beginning and are taking more than a year. They're harder problems to tackle. And that's true of a lot of our other partners as well, that these timescales can be multiple years to really start to make progress. And if you want to own that IP and you want to be able to leverage it when the time is right, it's important to start early.
Okay. So what about the other two examples? Maybe you can go quickly through them.
Sure. So the next page is showing just a machine learning problem of trying to do a binary classification. And here on the right, you see at the top is the quantum algorithm. The three below are standard classical algorithms. They perform similarly well. And again, the message here is we were able to run machine learning problems on quantum computers, not yet any better than classical, but giving reasonable answers. On the next page, we are using Monte Carlo techniques to price a financial asset. And the x-axis here is the number of samples of your Monte Carlo simulation. The y-axis is your error estimation. The red line is your classical Monte Carlo, and the blue line is the quantum algorithm. And you see the blue line has dropped below, which means lower error than the red line already at this 2 to the 4, which is 16 iterations of your classical algorithm. The catch is that we cannot extend the blue line further today. The quantum hardware is not ready. Whereas classically, you would run not 16 samples of your algorithm, but thousands or tens of thousands of iterations of your Monte Carlo algorithm. So the red line will continue much further to the right and drop back lower than the blue line. Again, the message is not that quantum algorithm is any better than classical today, but that we have real results and that the scaling is moving in the right direction. So we are optimistic that as the hardware continues to evolve, the impact will continue to grow. The next page builds off of this, and won't go into any detail, just to say that our colleagues at various banks, at the top Mizuho and MUFG, two of the largest competing banks in Japan, built off of the work on the previous page and published their own paper. And then JP Morgan Chase in the US picked up that work and together with colleagues at IBM built an extension. And so we see a lot of academic style research and collaboration happening across the industry, which is really encouraging in this pre-competitive phase. And we're keeping an eye on the industry to see when this might change. And this will become a topic, I think, for our third webinar, one of several topics we hope to cover then. Yeah. What does the industry look like today?
Yeah. So how can people get involved? We are almost at the end of our time together, like I already said, so we have to speed up a little bit. So how can people get involved in this new wave of computing, and what skills are required, Gilad?
Great. So the skills are quantum information, industry knowledge, and software development skills. IBM brings the quantum information experts, but we look to partners like Capgemini and also to the employees at our clients and collaborators to bring a lot of their own industry knowledge and software development skills. The actual skills needed, as we were saying, to go deeper are, again, probability, Python, and linear algebra. There are many ways you can start to get quantum ready. As we were saying, the systems are available for free through the IBM Quantum Experience. Qiskit is open source and free to use. And for those who want to go deeper, there's the IBM Q network and partnership through that direction. We don't just some statistics on usage that we have many systems available over the cloud, many net members of the IBM Q network, and many publications and many people using and contributing to the open source community around Qiskit. If we jump to the next page, please. So the IBM Q network is a set of collaborators, Fortune 500 companies, research, startups, etc. And I think on the next page, we should have a list of some of these members. So we're at, as of about a week ago, we're at 132 members across industries, across the globe, various sizes and flavors, and we're excited to be working with all of them on very different projects. If we jump to the next page, specifically for Capgemini, we are offering various ways to get that enablement journey started. And so one is a quantum basics course. This is an online course, covers a lot of what we've done today, as well as more detail, results in an IBM badge, and is really available to the entire team. And here's a little bit more information, and Michiel and team can follow up with you after the call and provide more information about how to access this course online. Coming soon, starting with the next webinar and building from there, will be also Qiskit training and Qiskit certification for those who are more technical and would like to actually start using the quantum computers. This first course is really just about being able to talk to your clients about what is quantum computing, why is it relevant, how should you think about it, who is playing in the field besides IBM, etc.
All right, so thank you very much, Gilad, for your extensive explanation. Maybe it is good that was quite interesting, Julian, that somebody started combing their hair in the background, which is a blessing from working from home, right? But maybe it's good that Cor and you discuss a little bit in the last few minutes that we have together, discuss a little bit about how Capgemini and IBM are collaborating. So maybe Cor, you can say something first.
Yeah, so happy to do so, Michiel. So to touch upon the topics just raised by Gilad. I think he provided all the kinds of ingredients that should get you excited about quantum computing, and especially also then this notion of this quantum journey. So there's a huge opportunity, I think, ahead of us, especially for you and for your clients, to get them quantum ready. And for that, of course, first yourself have to get quantum ready. And we have some thoughts around it, and I think also Julian will touch upon that one. So there was already then the course just demonstrated by Gilad, but there was also some other points that we are thinking of. So maybe Julian can also explore that a little bit more.
All right, Julian.
Perfect. So I think we have two ambitions, Michiel. One is to grow our community, and I would love to work together with Gilad and Cor on this. And to train people, to certify, to get this IBM badge. I got a few myself from the Qiskit challenge, which I thought was fascinating. So this is one of the fields which I'd like to work with you. First thing you have to do, join the teams. I will make sure that all the notifications, trainings, and all the people there will be there. So it will be a great place to come together. Second thing is, which I would love to work with you guys, is on developing our services around quantum technology. As you mentioned before, quantum technology is a whole stack. It provides, the lowest level is the hardware, but you go up with Qiskit frameworks. You need probabilistic theory and Python, and I think there we have a role to play together to shape with you guys, how these services would look like. So I think these are two things in which are very active, and I'm very curious to see how this is developing.
All right. So now, of course, more to come. And so we already have a next webinar that's already planned, going deeper, like Gilad and Cor already mentioned, on Qiskit. And then the third webinar we're also planning to go a little bit more into the applications and discuss, maybe have some more interaction around what clients would actually qualify early to start experimenting with. So that's all to come. Now, of course, also I believe there's a community already on Teams, and you will receive an email with the appropriate links there where you can find a lot of material as well. So please take a look. Otherwise, please join us for our next webinar. So that leaves me at the end of this webinar to thank very much Gilad for sharing, so being generous with your time and sharing all these insights and give us a little bit of understanding where this wonderful technology is coming from, but also a balanced view of that there's a huge promise, but there are still some breakthroughs and barriers to overcome, but still, nevertheless, it's extremely promising. Cor, thank you very much for joining us as well. Although you haven't spoken that much today, but you are our IBM Quantum Ambassador and one of our first points of access to all these technologies. And so people should know your name and reach out to you when they want to hear more. And you can help them navigate all the materials of IBM. And then last but not least, I would like to thank Julian very much for joining, for helping me moderate this session, for asking some questions. And then thank you for watching this webinar, and I hope to see you soon when we're going to take a deep dive into the Qiskit environment. Thank you very much.
Thank you, Michiel.